Alright, this is going to be the explanation of the Semester 2 Final Exam Review Problem number 2, which reads, a railroad car of mass 25,000 kilograms begins from rest and takes 40 seconds to reach a velocity of 4.75 meters per second to the right. After it reaches 4.75 meters per second, it collides with a second railroad car with a mass of 9,000 kilograms, moving to the left at 6.55 meters per second. The cars couple after the collision. So first, part A asks, what is the force required to change the first car's velocity from 0 meters per second to 4.75 meters per second? Now, since we know that the velocity is changing, we know that we can solve for the acceleration. Using this equation here, the final velocity is equal to the acceleration times the amount of time, which was given to us as 40 seconds, plus the initial velocity, which we know is going to be 0 meters per second, since the car is beginning at rest. So we have the final velocity, or 4.75 meters per second, is equal to the acceleration, what we're solving for, times 40 seconds, which was given to us, plus 0 meters per second, the initial velocity of the car. Solving for the acceleration, we have 4.75 divided by 40 seconds, which gives us 0.11875 meters per second squared. And that is A. This should not be equal. This is A. Alright, that's A. So now that we have the acceleration of the car, since we're looking for the force, we can use F net is equal to the mass times the acceleration to find the amount of force on the car that's required to change its velocity from 0 to 4.75 meters per second. And so we have that F net is equal to the mass of the car, which was given to us as 25,000 kilograms, times our acceleration, which we just calculated for, 0.11875 meters per second squared. Plugging that into our calculator, we have that F net is equal to 2,968.75 newtons. And that here is our answer to part A of the problem. Part B of the problem asks, what's the velocity of the railroad cars after the collision? And to find the velocity after the collision, we have to use momentum, because we know that momentum is conserved. Sorry. So, since momentum is conserved, we know that the sum of the momentum before and after the collision has to be equal. And so that means that the momentum of the first car, or we're going to call that P1, plus the momentum of the second car, P2, is going to be equal to the final momentum, or the momentum after the cars collide, after they've coupled together. And so in order to find the momentum, we have to solve for each of the car's individual momentums. Or to solve for the final momentum, we have to solve for the individual momentums. And so first we're going to solve for the momentum of the first car, which is going to be the mass, which is 25,000 kilograms, times its velocity, which was given as 4.75 meters per second. And plugging that into the calculator, we can find that the momentum of the first car is going to be 118,750 kilogram meters per second. The momentum of the second car is going to be 9,000 kilograms, which is the mass of the car given to us, times 6.55 meters per second, which was the velocity given to us at the time of collision. Putting that into our calculator, we can find that the momentum of the second car is 58,950 kilogram meters per second. Now, what may be misleading is that up here I wrote that the momentum of the first car plus the momentum of the second car is equal to the final momentums. However, since the cars are moving in opposite directions, what we actually know is that the momentum of the second car, since its velocity will be negative, moving in the opposite direction, that the momentum will also be negative. And so technically, this here should be negative 6.55 meters per second, and this should be a negative momentum here. And so what we're going to have is we're going to have P1, which is 118,750 kilogram meters per second, plus a negative momentum of 58,950 kilogram meters per second, is going to be equal to our final momentum, There. Solving for that final momentum, we get that P final is equal to 59,800 kilogram meters per second. So now that we have our final momentum, we can use this equation up here again, P equals mv, the momentum equals the mass times the velocity, to solve for the velocity after the collision. So we have the final momentum, which is 59,800, and we're going to be able to use the mass of the two cars together. Now that they're coupled, we have to add their masses. So we have 25,000 kilograms plus 9,000 kilograms. And we can abbreviate that, or not abbreviate, but we can say that that is 34,000 kilograms once they're added together, times the velocity, which is what we're solving for. And so, plugging this into our calculator, we have 59,800 divided by 34,000, which gives us that the velocity, the final velocity, is equal to 1.76 meters per second. And that is our answer to part B. Now part C asks how much kinetic energy is lost as a result of the collision. And for that, I'm going to flip the paper over to the back. Here. I'll rewrite the equation for you. EK is equal to 1/2 mv squared. And in order to solve this, we also know that energy is conserved, or that the sum of the energy at the beginning is equal to the sum of the energy after the collision. And so we can say that the kinetic energy of the first car, so EK1, plus the kinetic energy of the second car, or EK2, is equal to EK final, or the EKF, the velocity, the kinetic energy of the coupled cars, plus ET, which is our unknown, and that's the amount of energy that was lost during the collision, or what we're solving for. So to solve for the kinetic energy of the first car, we know that the kinetic energy is equal to 1/2 times the mass, or 25,000 kilograms, times the velocity, which we know to be 4.75 meters per second, that quantity squared. Plugging that into our calculator, we have that EK1, that should be 1 there, is equal to 282,031.25 joules. Now we're solving for EK2, which is very similar, but we use our mass of the second car, which is 9,000 kilograms, and our velocity of the second car, which is 6.55 meters per second squared, or meters per second, and that quantity squared. And we can solve that to be 193,061.25 joules. And now we can add those together to get our side over here, EK1 plus EK2. And so we have 282,031.25 joules plus 193,061.25 joules. And that will give us 475,092.5 joules. And that is the equivalent of EK1 plus EK2, or this half of our equation here. Now we can solve for EKF, or the kinetic energy of the cars after they've collided. And so we have that EK is equal to, or EKF, is equal to 1/2 of the mass of the two cars combined, so 34,000 kilograms, times the velocity of the final two cars, which we solved for back here, ignore that, back here in part B, 1.76 meters per second. And so we have 1.76 meters per second, and that quantity is squared. And we can solve that to be equal to 52,659.2 joules. And so now that we have both the sum of the kinetic energy of cars 1 and 2, and we have our final kinetic energy, we can solve for the thermal energy lost during that collision by subtracting our initial kinetic energy from our final kinetic energy. And so we have 475,092.5 joules minus 52,659.2 joules. And that is going to give us 422,433.3 joules, which was the amount of energy lost in the collision. And again, we can check our packet here on the last page, and we can see that right here we have the force needed to change the velocity of the first car as 2,968.75 newtons. We have the velocity of the cars after the collision as 1.76 meters per second to the right, which we should specify, although because it is positive and we used it, we calculated for momentum and we ended up with a positive number, we can say that it went to the right. If it had been a negative number, it would have gone to the left. And then we have last that 422,433 joules is the amount of energy lost in the collision, which we have calculated for right here.